Here is an image. I personally love this image because we can see the workers here who are intimately involved in this, this elaborate sunshade. These sunshades are made of essentially space blankets. They're the width of a human hair, and there are multiple layers of them. And then finally, when it's all put together, just before being packed into, of course, the Ariane 5. And now if we just go into OpenSpace here, we can now begin the program to really look at this deployment. So let me pull around and we see this is after launch. And so we're going to pick it up just after launch here. I'll back off just a little bit. And here we go. And we're launching in a time-lapse mode here. Here we are like 2 minutes per second, just to sort of get us flowing fast. And what we see Australia. I'm going to roll us around here. And we see a couple lines. Actually, we're sort of pausing here for a moment because there's a deployment that's about to happen. So let me just come down here. We'll see the first item of the telescope, which is deployed. All important. This is the solar panel, which will give it energy. And now, so I'll pull back around. That orbit you see going around Earth, we're now going at about 2 hours per second. That is the orbit of the Hubble Space Telescope. So at 300 kilometers, not far above the Earth. The other line is the orbit of the moon. We're now actually, we slowed down again with deployment of the high gain antenna, which we see the little cone down at the bottom. And now 3 days out, we've just passed lunar orbit. It took the Apollo astronauts 3 days to get to the moon. And so now we're deploying the pallets here, which carry the sunshade. So this is the forward pallet, and then the aft pallet will deploy as well. And so that we see they deploy very slowly. Actually, if we look back down there at Earth, far away, we can see the orbit of the Hubble once again. And one orbit takes an hour and a half, 90 minutes. The next thing to happen is basically, they call this the tower extraction, where we see that the telescope to the rectangular part at the bottom, the bus, is extracted into position. And then the next item that comes out is what's called the trim tab. There is enough size of the sunshade when it fully deploys, as we'll soon see, that momentum of the solar wind exerted on the sunshade is actually something that has to be counterbalanced. And so what we have is the deployment of this little trim tab, a momentum trim tab, off the aft side of the telescope. What's happening here now is what's called the mid boom is pulling out the multiple levels of sunshade. So that's what we see here. First on the port side, if we consider forward where the mirror is, and the mirror is now exposed, we can see that. And over on the right side or starboard side, we see the sunshades being deployed. And now they're being tensioned. And so bringing this into tension and showing in OpenSpace properly insofar as looking back toward the sun, that this sunshade is very important to keep the telescope in darkness or on the night side of the spacecraft, if you think of this wall of the sunshade. What's happening now is a secondary mirror is deployed into a tripod configuration. And the hexagonal mirrors are actually in a parabolic shape. And if I just come along the edge of this, we can see how it has that slight curve. So this parabolic shape is what is used to focus the light that's off to the target would be off to the right side of the image here. And the mirrors have to be fully deployed. So these are called the wings. There are 3 mirrors in each wing segment, port segment first, and the starboard or right segment being deployed. And then once this is fully together in its observing configuration, this will allow the parabolic shape to be focused. All that light will be focused on the secondary, which is off to the right, and then that mirror sends it into the sort of box cone that we see, which is the entryway into the light into the instruments off the back. And there's sort of four major instruments, imagers and spectrometers. And I just would like to mention for a second that while we think that this is a huge mission for NASA, the European Space Agency is not only launching the telescope, but they have an instrument on board, as does Canada. And there are 22 nations from the European Space Agency. Add in Canada, the United States. This really represents the effort of 24 countries. And so this is a big international effort. And it's launching around this time where a lot of nations around the world celebrate different religions, really celebrate the gathering of the light, to bring the light back. And as we have the shortest days of the year in the Northern Hemisphere. And so it's sort of appropriate that at this time of year, perhaps, that we're launching this wonderful telescope to gather the light. And I wanted to point out, this sort of distance that the JWST is going to. I mean, we saw way down there at the Earth is where the Hubble orbits, and that we could get the space shuttle up to it back then to service it. But we can see now that that ring shape back there is the orbit of the moon, which is 250,000 miles. JWST is going out to a place called Lagrangian 2, and this is a point of sort of gravitational balance, if you will, between the influence of the sun and the Earth, and it's in line with the sun and Earth. And so this is this Lagrangian 2 point, and that JWST, we see its trail with respect to the Earth. But in a moment, what I'm going to do is speed up time here so that we can actually see what it does in orbiting this location out in space. Let me actually pull out just a bit. I want to turn the moon's orbit back on, as well as just advance time. I'm going to advance quickly at like a month forward. We've changed the orbital path with respect to the L2 position. We can also see the orbits of the other planets.
I just want to say Carter went through pretty nicely and quickly in some ways that deployment of James Webb. And you might be reading a lot of articles right now of how astronomers are like nervous about all those steps that we just saw in that deployment. And that's in part because these are a lot of moving parts. And that's part of this big advancement and why it took a while to get James Webb ready. It took a while for it to get approved because people thought it was too complicated. But here we are. It's going to deploy. It'll take about 30 days of terror of astronomers all hoping that everything deploys until we get to this nice point, Lagrange point number 2, about 1 million miles away from our home planet. And once there, they'll test the instruments, and that's the part that we're kind of at right now. Carter's got us now moving through time a little bit, where you're seeing the orbit that the James Webb Space Telescope would be placed into when it gets to Lagrange point number 2. And I think you've got us moving in time now, right, Carter?
I do, and we can see that the moon goes around the Earth every month, one month, and that we see that over the course of the year, the James Webb somewhat slowly orbits this sort of gravitational balance point, the Lagrangian, and creates a kind of interesting sort of saddle shape. But it won't be lonely out there, because there are other missions. Jackie's involved. You're involved with the Gaia mission, Jackie, and there's also the Planck satellite. So this is a place where other observatories actually sort of orbit this point.
Yeah, it's a really nice place to orbit, and we should get right into why are we going there. Yes. When you keep hearing that JWST is the successor to the Hubble Space Telescope, which orbits just about 300 miles above your head. And astronauts have gone up and fixed it and replaced it, and that was really nice. But that is not the case for James Webb. We had to launch it way out here, 1,000,000 miles away, because we wanted to go to a place where it was going to be nice and cold. Now, James Webb operates at a different wavelength than the Hubble Space Telescope does. Hubble Space Telescope operated at wavelengths that were kind of central to, like, you could understand, like your eyeball. It was optical. And then it had some ultraviolet light and a little bit of near infrared light that Hubble could do. The James Webb Space Telescope is all about the infrared, all about it. Infrared, infrared, infrared. That is James Webb. And Carter's got us kind of situated so that you can see that shield that we're all so nervous about, as it's going to be pulled nice and tight and taut. This heat shield is protecting it from the heat of the sun. Now, Carter's got us set up so that you can really see that nicely from this perspective. The telescope will always have that heat shield between it and the dangerous heat from the sun that we don't want it having anything to do with our telescope. Right, Carter?
Right, and I'm going to leave the orbit of the moon on because it sort of helps us locate where the Earth is. And so we want to keep, yeah, exactly. We want to keep the sun on one side and the instrument on the night side of that sunshade. And so we thought we would show you now actually sort of the pointing of the telescope and what it sees. And remember, I was sort of talking about the parabolic nature of the mirror, the curvature. So it focuses it. So if we now just turn on some parallel sun rays, we can, or parallel light rays, I should say. The sun is coming from the side. But if we now look down in perspective, we're going to see that it looks off to a part of sky. And it's like, you know, it's like if you walk down a railroad tracks and you see them converge off at a vanishing point. Well, there's also a part of sky that we're delineating now that is in light gray. And this illustrates the safety portion of the sky that can be seen. And it's actually kind of like a big donut of the sky, if I just sort of twirl around here. And this is because, well, on one level, you can understand that with the sunshade blocking the sun, that we don't want to be pointed to the sun. So the sunlight over here. But then also, if it tips too far, then sun comes in on the instrument module, which is where all the scientific instruments are, and they cryogenically cool the instruments to have greater sensitivity, especially in the wavelengths it's going to be looking at. In fact, Jackie, you can talk to this, but I'll just point out that the yellow mirrors that it have, it's more sensitive to the red. And and why is that, Jackie? And so this really gets to the heart of what this mission is really about.
Yeah, so let's dive into what it is that James Webb is going to look like and how it's going to do it. And as we do this, I want to explain to you what the sky looks like to you versus what it's going to look like to the James Webb Space Telescope. So Carter's got us with this nice view of the Milky Way. It's kind of getting stretched in front of us here. There's James Webb. The Milky Way is stretching around. That's the this galaxy that we live in, the Milky Way galaxy. And you kind of look towards it, and this is what it would look like in optical light if you got to a really gorgeous night sky. Many of us maybe are in New York City. We can't see this all that well, but from dark skies you can. And now as you look, you can see there's like all of these dark spots along the thick part of the Milky Way here, where there looks like there's an absence of stars or an absence of material. But in fact, it's not an absence at all. What's happening is that between your eye and the stuff you want to look at, there's a lot of dust. And the dust is absorbing the light that you want to see in the optical. So optical is not good at looking through dust, but go to the wavelengths that James Webb is going to look like, and the whole picture changes. So Carter just switched for us the sky, or is about to switch for us. We've switched it now, right, Carter, to the 2 micron all sky survey. Now this was it's an all sky image 2 telescopes on the ground looked at a wavelength to show you what the entire sky would look like at a wavelength that James Webb is all about. So now you can see that all those dust lanes that we were looking at before, where they were dark and there was nothing there, they're getting filled in. And this is near infrared light. So this is more of the light that if you take your hands, slap them together and move them real fast and then put them close to your face, you'll feel heat coming from your hands. That's because you're basically glowing at the wavelengths that you're seeing here. And James Webb is going to look at that to see some of this structure of what's in those dust lanes. Now, Carter, let's switch one more image to the wide field infrared survey explorer's view to the longer wavelength that James Webb is all about. And look at this structure you start to see. Amazing now, from starting at the optical down to this wavelength of light, which is called mid-infrared. And in this, now look at all that structure that all of a sudden you get to see, where before you saw nothing because you couldn't see through the dust and you couldn't see the dust. And what these wavelengths do for you is they open up the ball game on dust. They open up this ball game to see through to the kinds of things that are glowing at wavelengths that your eye cannot see. So notice all this gorgeous structure that you see. Carter's kind of moving us around the Milky Way, where you get a lot of young stars. So that's going to be a big target for James Webb. You're going to see a lot of dead stars. Dead stars have a lot of shells of dust around them. And so these are the wavelengths. Now, these 2 surveys, the 2 micron all sky survey, which we showed first, and this one, NASA's Wide Field Infrared Survey Explorer, are the exact wavelengths of James Webb. It's just that they were not as powerful, very much not as powerful. And this is giving you kind of a full view of what the sky looks like. And what happens now is all of the scientists have made decisions on, like, we know that the sky looks like this at these wavelengths. Now with James Webb, we can zoom in and really say, let's look at these objects in detail. Let's really figure out what's going on with them, because James Webb gets us deeper and gives us a really gorgeous spatial extent to what might be happening because of dust. Just keep thinking about dust when we start showing you things, because that's going to be a really big factor throughout.
I thought I would just give a little bit of planetarium orientation here, especially at this time of year, when we can see the beautiful constellation Orion. And what we were seeing with the WISE instrument in the mid-infrared was we were seeing all sorts of starburst formation. Jackie mentioned that, but what we see, of course, is the 3 stars, the belt of Orion, and the constellations. We have them named here, but also just to sort of aid us in this, we thought we'd also show you how astronomers, Jack Eden talked about this better than I, but how this sort of real estate of the constellations and how the sky is divided up to identify objects within these areas.
Yeah, and we're going to use that location map of these constellations to help guide you to where we're going to point. Because what Carter and I did is we selected a few case examples to show you the powerful first light objects that James Webb is going to look at. And so now with OpenSpace, we can kind of move around and show you how this telescope is going to point and what it's going to look at in its first year, basically, of operation. And one of the things we'll show you, I have to say, I'm one of the scientists that got time in the first year of it. And so get ready. I'm gonna tell you all about what I get to look at with it in the first few months. So I feel particularly attached to this telescope right now. But we're going to start with the farthest things, and then we're going to take you back in closer and closer. So Carter, I think we should start with our first object.
Yeah, I just want to say that that what we're looking at here right now, it makes it seem like, oh my gosh, we'll only see this band of where it's light. And I neglected to just say that this band of visibility on the sky actually moves as we move around, as the Earth moves around the sun. the L2 moves around the sun, and so the instrument moves around the sun. So that's our setup. Because Jackie, you're gonna give us our first target now, and I'll try to bring James Webb, the visibility of the sky, back to where that target is. So.
All right, yeah. So we're going to pretend that we're able to basically be the telescope operators right now and point the thing towards where it is actually going to be pointing when it launches and is successfully operating on the sky. So Carter, first object is going to be the Hubble Ultra Deep Field. And I think you could set that up for us with, we're going to be switching into a different mode of OpenSpace right now, and a special kind of component that has been built into it, something called the Worldwide Telescope, where we're actually able to create a little window that lets us zoom in on, say, the images that you're going to see when the James Webb Space Telescope points at the area.
And I'm also just going to come in. You'll see my cursor. I'm going to enlarge this field, but yes. This OpenSpace, by the way, if you want to run this yourself, OpenSpace is freely available at openspaceproject.com. We are open source, NASA supported, and it's also a collaboration between the University of Utah, and New York University, American Museum of Natural History in the lead, and then also last but not least, Linköping University in Sweden, who we've collaborated with since the early 2000s. And so with this, we can now zoom in to look at this patch of sky where basically on ground-based telescopes, we saw nothing there. And so, Jackie, how long do we stare at this part of sky? This is the Hubble that took this picture. But,
yeah, so Carter's got us pointed in the direction of where the Hubble Ultra Deep Field image, and that's what has been pulled up here. This is what it looked like when Hubble looked at it. They spent what amounts to 10 full days staring at an area of the sky that was otherwise just blank. Nothing was there. They decided on a really nice, beautiful, dark patch of sky, and then just basically let the shutter stay open and gather as much light as they could to see the farthest that they could and what all of the objects in there might be. And when they did, it was pretty shockingly gorgeous. And Carter's got us zoomed in. Look at all of those objects. Those are primarily, all but just a handful, they're galaxies. And they're galaxies that are close to you. And then there's galaxies that are at the edge of what we call the observable universe. So they show the farthest back that we can look. Hubble has taken us this image, and we study what we see in this exact image and what the galaxies are doing. So you can see galaxies up front. Carter's kind of bringing one in here. The ones that are bigger and brighter and like gorgeous in detail and look nice and spiraled, those are closer to us. But then you'll go to ones that look very red. Now, the reason why they end up looking so red is because it takes so long for their light to arrive at us. They're red shifted. You might have heard of this phenomenon where light is red shifted. And as a result, if you keep looking to redder and redder light, you can, in fact, look farther and farther back in time at what was happening. And that's one of the primo, very, very exciting things that James Webb is going to do. It's going to take a very deep look at this exact region of the sky. They're calling it W deep. And it's going to get 121.8 hours of James Webb time to stare at this field, to try and look at the galaxies that are red shifted beyond what Hubble could see. So what we call first galaxies, and then to really study the light of the galaxies that are all over this image, that we already know are some of these first galaxies. And we're going to be able to look at what kinds of things the stars were doing, because we get to see the dust. Follow the dust, and you're basically following the stars. What the stars are doing is what the dust is telling you that they're doing. So this image is going to be called W Deep, and you'll have to look out for it in the first year of James Webb when it's launched. I guarantee you, W Deep, the James Webb version of the Hubble Deep Field, is going to show up all over your social media as we get this infrared image of the deepest image we've ever taken of our visible universe. So it's a really exciting prospect. And this is the farthest thing that we're going to show you that James Webb is slated to immediately start giving us information on.
I thought I'd just emphasize that any star that we see has kind of a crosshair to it because of how the secondary mirror and Hubble is suspended and so forth. But this illustrates there are not many stars here at all. Every one of these little points, these are galaxies. And so we chose this area because of its lack of stars, and there's another star, but there are very few foreground stars. These are in our galaxy. And then we're just looking at this tapestry, and it's, even though it's a small part of the sky, and you can see that it looks like a point off there over on the right of where the James Webb is looking in this illustration, the visualization of this, is that just imagine that if it looked right here, it would also see a tapestry of galaxies. But this is just a small part of the sky where they looked, and so its ability to sort of back off using the Worldwide Telescope. So Jackie, I'm gonna size this down, and I'm just going to for a moment just use Orion here. And I was talking about how this zone of visibility precesses across the sky. So I thought what I'll just do is I'll just jump by day here. Let's go ahead to from November 22nd, and we're stepping forward. These dates I'm saying were actually a study of what the mission would look like with an anticipated launch date of 2018. So if I'm giving time here, it's really just I'm moving like an increment of a day at a time. And think of this: we go around the sun in 365 days in a year, and there are 360 degrees in a circle. So as we move just under a degree a day, and so that zone of visibility moves about. Okay, all right, Jackie, let's hit our next target.
All right, so next category of object that the James Webb Space Telescope is going to be focused on is called starburst galaxies. So let's go to M82, Carter. I know this one is a favorite of yours. And for those of you on here that might be amateur astronomers, you might recognize this name, M82. It's the 82nd object in the Messier catalog, a very popular catalog of objects to use for your nighttime observing telescope attempts to like look at really cool looking things that you can see through the telescope. Some of these you can see through binoculars really well too. But M82 is the
right
closest,
off the Big Dipper.
Yes, right. So it's great for us in the Northern Hemisphere, as the Big Dipper is our circumpolar constellation. So you know you're looking north. And that's a great point. Carter has us set up so that you can see where in the sky we're looking at. And so he's got us pointed towards the Big Dipper. There it is, M82. This is going to be an awesome one for James Webb to look at. And so this image is a composite image that Carter has pulled up. Here, it's got a couple of different wavelengths of light that's all being showcased. So what this thing is it's a galaxy. You can see it's kind of like edge on there, or we're catching it at a slight angle. It is the closest what's called Starburst Galaxy. And this thing, it's called Starburst Galaxy because it's got a burst of star formation going on. And that anytime you get young stars, you get a lot of dust, like a lot of dust. The dust ends up being the precursor to the new stars, but it's also kind of left over and all around in a young star forming region. So I think Carter just moved us into an X-ray image too. So you're kind of fading it in and out right now, right, Carter?
Yes, and so this is the X-ray image, and And this shows where very high temperatures are, and then where the young stars are forming. And then we can kind of go back and forth, again, using Worldwide Telescope's API that we're sort of embedding in OpenSpace.
Now, so interesting, the James Webb is going to stare at this object, M82, for 42.7 hours. Again, a pretty lofty amount of time dedicated to studying exactly how the star formation works in this. Now, this Starburst Galaxy very likely is the result of two galaxies that have just collided. And that's part of why it has this enhanced star formation. And we think this is how galaxies built up to become big-sized things like what we see around us. So in the early days, galaxies were hitting each other and were building and building and getting larger. Now, this object here, M82, is about 11 million light years away from us. So we've come way in from the edge of the observable universe, which the W deep image had us out at. And James Webb is now going to be looking at things like this. There's a lot of starburst galaxies that are of interest here. And you've kind of pulled this out so we can see this other galaxy, right, Carter?
Yes, M81. And if you have a backyard telescope, and I grew up in New Jersey, not far from New York, so you could see it from there. But if you know where to look, or you aim your telescope these days with just computer control, and these are really amazing because you can just barely see in an 8 or 10-inch telescope. You kind of see the spiral nature of M81, and then you see this strange object of M82, and you do see how the light is interrupted in the center. So this is sort of like what you might see in a backyard telescope.
Yeah, cool. And so the thing about M82 is that it's got what's called young super clusters in it that are all enshrouded in dust. So we haven't been able to see them yet. And they are the engine of that starburst galaxy. And so JWST is able to open the window and let us see what's happening.
They're actually, this is a Hubble picture right here, Jackie. I'll just zoom in really close. I meant to bring this one up earlier, but there you can see how this dust almost looks like the way we see dust, in our own Milky Way, like we saw at the beginning of the program.
Right. And this has like 10 to 15 times the star formation rate that a galaxy like ours has. And we want to know what is going on in those dust lanes. And JWST is going to give us access to that info. So we're going to get some info on how this star formation process works in these galaxies. Okay, let's move on to the other thing that dust will tell us, and that is dead stars. So why don't we go to the Crab Nebula, Carter?
Okay, awesome. Let's do that.
Another favorite object.
There we go. And let's just navigate over to it, and let me center the crab in our Worldwide Telescope. There we go, and it's a beautiful object. There it is.
Nice. Now, the Crab Nebula, for those that aren't as into astronomy, it's a fun name that we give sometimes to things that are older that we've been looking at for quite some time. And so they got really nice names. And Crab Nebula has a particular shape to it that invoked the name. What this thing is the remnant of a star that was probably like 10 times the mass of our own sun or so. And it exploded in a supernova. When that happened, it's, debatable, but this thing lies about 6,000 light years away or so. The distance to this is also a little bit debatable, but look at this detailed structure that you're seeing here. Carter's kind of moving through images that have been taken over different wavelengths with different telescopes, but see all that structure? It kind of looks like filamentary structure. Oh, and now he's zoomed in on the central area of this particular object where you really get a chance to see the villain of what happened here. Because at the center of the Crab Nebula that stretches several light years away from a central thing, which is the leftover star, It's a pulsar that's spinning, spinning, spinning rapidly. And it's probably got about maybe twice the mass of our sun, all compacted down to a radius of about 17 miles. So it's a really dangerous object.
Manhattan.
Right. And so James Webb is going to stare at the Crab Nebula for about 23 hours to look at all of those lanes all this structure. So you kind of have it here, Carter. It's a good image if you take the central region out. Like you can see these like needles that are kind of coming off of some of this shell-like area. And what we want to know and understand is how fast gas is moving, how fast the dust is moving in these areas, in these kind of like threaded out areas, because this is where this massive shock wave went off when the supernova happened. And you've got chemistry that's happening. This is where really interesting elements might be for us to study and how they get distributed across this nebula. Supernova end up giving feedback to the rest of the interstellar medium, all of the area that forms the next generation of stars. And so with the James Webb, we get to see that dust and we get to see that chemistry on what is left over after a star dies. And we'll be able to see the results of the shock waves that really hit the leftover materials, because what blew off that star is everything that was left, and then just started slamming into stuff left and right. So Crab Nebula, another prime target. And I guarantee you will be seeing the James Webb Space Telescope's image of the Crab Nebula after it is taken, because it is such a famous object.
And I have a warning on my software saying I'm violating the sun condition here because I'm looking off the allowable band. But we're sort of allowing us to now look at these various places on the sky. So what's next, Jackie?
Well, we're going to go to another object that's really, it's going to be the opposite of something that's a dead star. It's going to be a young star. We're going to go to HH212, Carter. It's a Herbig-Haro object. HH stands for Herbig-Haro. It was the name of two different astronomers that discovered this particular, or at least not necessarily discovered, but were the ones to really characterize this class of objects, which are very young stars. So that's another major topic for the James Webb Space Telescope, to look at young stars, because young stars are enshrouded in dust. Once again, dust, 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 dust. And HH212, look at this thing. This thing is insane. This image was
right there in Orion, right just off the belt of Orion, as you can see here. Yep.
Yeah, and that's no coincidence, because Orion is the area of young star formation. And HH212, Herbig-Haro 212, is a very, very, very famous young stellar object. And this is also what's awesome. So Carter, as you kind of zoomed in, that was actually an image from another European space observatory telescope with an instrument called Isaac. It's an infrared image. So this is a real precursor to what we're going to be able to dig into major detail with James Webb. And so look at how long that thing is. The orientation is such that we're looking at this thing edge on, which is fantastic, because we live in a three-dimensional world. We could have gotten any orientation here. If it had been facing us and the jet was coming towards us, we wouldn't be able to see the length and breadth of it. But with this length and breadth, Carter's kind of zooming into the central region, which you can also go into extreme detail with specific telescopes. This is, I think, from the ALMA telescope that Carter's just moved into an image there. But this longer image here, notice how there's these bow shocks where there's the star, newly born, is pulsing. It's giving off rapid amounts of energy. And as it does, it sends a lot of energy out into the material that's kind of left over from when it formed it, as well as like the regular interstellar medium. So it slams into it and you get a bow shock, similar to how the solar wind creates a bow shock around the Earth. Look at that structure. And so James Webb is going to get, I mean, that's amazing, right? And this is, like, we're looking at a zoomed out kind of view.
James a lot of stuff going on out there.
Yeah, it's running into material. And what we want to know about is what those shocks do. And so James Webb is taking a high resolution spatial look at this particular object so that you'll be able to see what the small scale shocks are doing across the length of this thing. This is how stars form. This is like literally the picture of star formation.
And the dust is
we're
the
gonna
star
study it.
stuff that makes us up.
Yeah, that's right.
And what's amazing too, Jackie, is that the star itself is embedded within that disk, which we see really just edge on. So it's you know, we can't even see the star is right in there, and it causes all this havoc in the neighborhood. Amazing.
It's true. Yeah. I mean, this thing is only a few million years old. It's a baby. It's a baby star, and baby stars are violent. They have a lot of energy because they're just being born. So James Webb is going to tell us exactly what kinds of dangers these young stars bring to the table. All right, let's go.
I shouldn't do this, but there's just north of it a little bit. There's another object that's a series of beautiful jets that well we'll show it another time. But it's gorgeous because it's like 3 different jets together. It's
I can't tell.
Too much stuff to see. There's the Horsehead Nebula. It's beautiful. It's just off the belt of Orion. So yeah, we're next, Jackie.
All right. We're actually going to come into the last 2 objects, and I wanted to make sure I could tell you about the kinds of objects that I'm going to study and that I'm very excited about. So Carter, let's take us out of worldwide telescopes so that we don't break open space. And we're going to show you the things closest to home, because HH212 had us at, how close were we to Earth? We were 1,300 light years away at that particular object. And now I'm going to take us real close, because the other thing that James Webb is amazing at is looking at individual objects and their atmospheres. And the objects that I study are called brown dwarfs. They're in between stars and planets. So they're not massive enough to get nuclear burning going at their core, but they're more massive than like Jupiter. And so they get a little bit of heavy hydrogen burning, and they typically are found without a host star, which is a good thing and maybe a bad thing. The good thing is that you can just take a telescope and look right at them, and you don't have to block the light of a star. And so I got time for 20 hours of James Webb Space Telescope to stare at a handful of brown dwarfs that I think are going to show us the kinds of diversity that you should be able to see in exoplanet atmospheres. So Carter's kind of moving us around. And what we thought we would do is turn on, do you have on the 2-mass full image, Carter?
Yeah, let's do that. And what I'm going to do is I'm going to get rid of the constellations for a moment. And
yeah,
there we go. And we'll turn 2-mass back on. Now we see the orbits of the trails of the our planets in the solar system, and that's going to help us kind of just keeps us kind of locally oriented. But let's now turn on 2-mass. There we go.
So 2-mass, which was the near infrared catalog that we were talking about earlier, is was used to find a lot of brown dwarfs. You had an all sky survey and you look for objects that give off the majority of their light in the infrared. So we found a bunch of them. Carter, you can turn on the full catalog. There's thousands now that we know of, but the ones that are closest to the sun, and by the way, the 4th closest and the 3rd and 4th closest objects to the sun are brown dwarfs, both of which are major targets for the James Webb Space Telescope, because these objects shine like light bulbs at the wavelengths that James Webb has. I'm going to end with this idea that the James Webb Space Telescope is going to look at objects like these that are scattered across your sky. You can't look at every single one of them with James Webb because it's got a very, very difficult to point mechanism, as Carter was kind of showing us earlier. So it takes a lot of time to slew to an object. So you're better off really targeting your favorite objects or the best ones for telling a story. So we are going to stare at a handful of these brown dwarfs with first year, and I will be able to come back and tell what's in their atmospheres. We're going to be doing that exact same thing with exoplanets as well. So there's a couple of exoplanet targets for which we are going to study them in detail and be able to say something about what is in the atmospheres of those objects. So that's the end part of our presentation, of saying, like, James Webb is going to take us everything from the first galaxies, the galaxies that are amongst the first ones to have formed, what they looked like, what the star formation process looked like for them, how that transferred into what we know is happening today in the universe, to young stars and what they look like as the new age, the new millennium, the new millennials of the universe, to the atmospheres of objects that we know may be life-bearing, some of the exoplanets, or may tell us about what worlds beyond Earth end up looking like.